Okay, so this afternoon, we'll be looking at 3D equilibrium of a rigid body. All right, so this is the height of the 3D that we'll be doing. After this, then we'll go back to regular other types of problems. All right, we have shear force bending moments after this topic. And then we have centroid and moment of inertia. So we're actually winding down. So we have, call it 3 main topics after this. All right. So remember, this is an exam topic. A question by itself will be coming. All right. So this is 3D equilibrium of a rigid body. All right. So let's jump into it. So typically we're going to be looking at reaction at a 3D support at identify support reaction in 3D and then draw a free body diagram and also how to apply equilibrium equation. So this is what this exercise is all about. So you're going to look at application, support reaction, and problem solving, basically. So let me see if I'm at the right one. Let me see if this is the right slide. Don't want to jump too far. Make sure that I'm in the right slide. Okay. Yeah, so I'm gonna run into this one, but all right. All right, I'm not gonna use this slide. Hold on. I'm gonna change the slide. I'll do the slide afterwards and start with another one. This one is a little bit more. So I'm gonna start with B before I do A, and I know why. Right? So typical, as we say, look, we're gonna be looking at reactions, right? And draw a free body diagram. So here you can see you have what they look more like a lift, right? You know, those lifts that you use on buildings to clean windows and so forth. So this is known as a rigid body. And so there are 3 points that you have load support, right? So you can see you have the hydraulic between BC, and then you have another pin joint or hinge at A, all right? Now, for similarly, you could have a platform, right, on a rig, oil rig, and what you have here is what they call the platform section of the oil rig. These are cables, and it is supported at a point. Now, this is showing you the space diagram of how it is supported, that you have up 2 pin joints there. So we're gonna look at what is pin joint shortly again. Some of you would have been exposed to that already. We're gonna look at it again. And here you have the cable, so you can see support. Also, we look at the center of gravity of this in terms of all of the forces that is acting on the frame. Now, this is now your free body diagram, so you can see where you have the pin joint supported here. At this particular point, we can draw all the reactions at this point. So you have 2 reactions. And then in the cable, you have all the force going in. So we're interested in the force in the cable. So the force in the cable here is going up. The weight due to gravity is coming down on this. So you have this, what they call an ideal model, and then a free body diagram. That's what that is really showing you. For this now, this is, you have a steel beam, which is being supported roof joints. So these joists, 3 joists are resting on it, that you know support your type of roofing that you have. Sometimes timber roofing with the zinc sheet. And some persons even have some beams that runs into concrete. And most concrete have beams that run into it. And then they form some form of matting up there, and you cast the whole thing to give you support. Now, we can look and see that is what we call more like your space diagram. And below you have what we call more like your free body diagram. It's not so much a free body diagram because it's not a line diagram ideally, but it shows you, it's pretty much more like the space. So the other one is like a picture, and this other one is more like the space diagram. where it show you the forces on it. Also show you that you have a reaction at A, which is a pin joint, and you have a roller at B, which is a support, right? So we run on along. And so we are able to compare the condition of rigid body. So in this case, you have this is like a particle, right? So we have force on the particle. So there are contrast force on a particle and force on a rigid body. The force on a rigid body, right, are not usually concurrent and may cause rotation, right? So it says in contrast to the particle, the force on the rigid body are not usually concurrent and may cause rotation of the body, right? Which is due to what? Moments applying to it. So for the rigid body, you have equilibrium, the net equilibrium, net forces and net moment on the system, right? So at any point you can find the net moment and also the net force, which would give you the resultant of it, and to see whether or not the resultant is zero. If the resultant is zero, then you know it's in equilibrium, right? In that system. Back to this system here, we said that it actually a physical system. First, you need to create some ideal model, and then as we need to draw some free body for the system. All right, so you can see the free body is being drawn from here. And here we can now apply our equilibrium equation, and we're gonna solve for some unknown in the system. All right, so that's typically what we do. And here's another system. You have a cantilever, a load is on it, but it is pinned to a wall. Pinned to a wall, what happens when a load is pinned to a wall? How you analyze it is totally different. So normally we put free support matter. So it's like a bridge between 2 points, and you have the bridge rest down, and it has support at either side of a river. Let's say a river, you know, a wide river, and you have a bridge, which you often have to travel on. And so this was different. It is one side is pin and one side is free. So this is more like a cantilever, right? But probably longer. You have a beam. So here we say we draw some outline and shape. You imagine the body to be isolated or what? Cut. So you imagine that you chop it off right at A. What are the forces? You chop it off at A and you analyze what is the stress going on when it is pinned there. So really and truly, what is happening when it is pin jointed there, you have two reactions, one in X, one in Y, and you also have a moment, right? There's a moment there in that truss, and so you have, and now also we have to represent the other external forces on it, as you can see too. So you draw them, and you are able to look at all the external force and the coupling moment typically, and apply load support, right? So you have load support at B, and you have the weight of the body, right? And so the next thing you look at, you're gonna label the load, look for the dimension, and then now you can look at all the known forces, and the coupling should be labeled with their magnitude and direction. So you'll go ahead and do that, and then also you identify all the unknown force coupling moments, and then you use your labeling respectively properly. So for example, in this one you have AX and AY, and then you have MA, right? So you need to label your unknown. Now, how did we get to the support? No, there's a systematic way how we know what support to put at what point for your support reaction. Huh? It is very systematic. And systematic means if you look at this one here, you will see that you have a cable pinned to some metal, right? And so it will show you that there's a force coming off on it, one single force when it is pinned there in that cable. What about an inch? When you have a pin joint, you always have two forces, and the other figure showing you over here your resultant force of the two. The fact that you have X and Y, it means that you have a resultant for both of them. And so it shows you, phi shows the angle of the resultant force. Look back up top now. We have a roller that is rolling in an inclined plane. Whatever direction that you're rolling, you will have no reaction in the direction that you're rolling. So if you're rolling along the inclined plane, no reaction, but you will have reaction perpendicular to the plane, which you can see this is right angle to it up here in the roller. Right? I hope you are seeing my pointer. And then the last one again, cantilever again. This is how we know to draw the cantilever on this frame around here. Right? Look, you see how we know this is pin to here, and similarly, this is pin here. So we know that there are reactions going both on this body here. So one is going out, one is going out. And look, they are going opposite direction here. So those are the forces being anchored on this. So therefore, your reaction must go opposite to this. The black showing you the reaction. Red show you the force that is applied to it. Black show you the reactions. And simpler, you see your resultant force. So that's what that is showing. So generally, it is said that to prevent translation, which is what? Moving in a straight line of a body in a given direction, then a force is developed on the body in the opposite direction so as to prevent a translation. And similar, if the rotation is to be prevented, you must have a coupling moment is exerted on the body. So what prevents a rotation? A coupling moment. What prevents a body from sliding? It is restrained, right, by a force in the opposite direction. So some of you know about friction. So there's a frictional force, but in this case, it's not frictional force. Something is actually preventing it. So it to stay in equilibrium most likely. All right. Or after a while, it's released depending on the force. So these are similar. You can see them here. So these are the connection. See the reactions similar here. The connection, and the different forces that you have. You can have it in either direction, depends on the frame. And similar, you see these here, right? So you're familiar with these. And similar, you have the roller, perpendicular, one force. Anytime you have a roller, so this is a roller, look at the type of roller, smooth. This is a rocker. Look at that. Smooth contact surface. That's how it look. This is known as a collar. So for a collar, it's different. So it's being perpendicular here. Now, look at this one carefully because you're going to come to these. These are all one unknown, right? What about these here? Here now you have a pin joint. So you know, once you see a pin, two reactions. One in the X, one in the positive Y. And there you see the resultant. And then you look at a color again. And the color will represent that there's a moment on the body. And there's a reaction perpendicular to the direction that you can move the color. Okay, you can move the color along here. It's a smooth color, so it can move anywhere along the rod here. So therefore, you will not have any reaction that way, but you'll have a force perpendicular to it, and you'll have a moment. Number 10 here, this one again, you saw that before. You'll have a moment, and you'll have two forces, and so you can relate to those. How many reactions you have there? This has 3, this has 2, that has 2. And you need all of these so in order to solve these type of problems. So a body is subjected to a system of force that lies in the XY plane, as you can see here. When in equilibrium, the net force and net moment acting on the body is said to be 0. So this is a 2D condition and can be represented by three scalar equations. So the scalar equation that we have introduced you to so far is the sum of the forces in the X, sum of forces in the Y, and sum of the moment is 0, right? Where point O is any arbitrary point. Running along. Here you have some forces on a point A here, similar B here. And what happens here is that all of these forces, these can give you a resultant force here. This can give you a resultant force. And then now you get FB is equal to minus FA. So the solution to some equilibrium problem can be simplified if we recognize the members that are subjected to force at only 2 points. Right? Force only at 2 points, at point A and point B. And if you apply the equilibrium equation to such member, we can quickly determine that the resultant force at A and B must be equal in magnitude and act in opposite direction along the joint pointing A and B, right? So that's what that is demonstrating to you. So look at this now. Now you have a truck with hydraulics on it. So you can look at this one here. So you have a heavy equipment. You have a joint here at B, A. Can you see those? And over here, there's a A somewhere over here. It's a A right down here, so at the bottom of this lift. This hydraulic. One at B, one at C. So C supporting this part here by itself. So same equilibrium equation at A and B. In the hydraulic lift, there's tension force either side. So that is in tension. It's showing that it's acting out of the point, and it's actually going in. The reaction is going away from there, from each point where the load is applied, and so you can see the line of action for these, all of these similarly. As it implies here, two force members are force applied at only 2 points on the member. For any two force member to be in equilibrium, the two force act on the member must have the same magnitude and act in opposite direction and have the same line of action. So you can see the same line of action directly along the line joining the 2 points where these force act, provided that their weight is negligible. So the weight is negligible, we assume that. And so the method of solving these equations, one is given to establish some sort of X and Y coordinate system, draw a free body diagram, use your three equilibrium equation for your unknown, right? And so also there's something that you need to know about statically indeterminate system. What is statically indeterminate system? It is a system that has more unknown that the equation, the regular static equation, cannot solve. So we cannot solve these problems using just statics. You have to get into other type of methodology to solve them. Once it is statically indeterminate, a lot of structures are built statically indeterminate to give it extra strength, right? So they are not simple frames. The order in which we apply equation may affect the simplicity of the solution. For example, if we have two unknown vertical forces and one unknown horizontal force. So it depends on the problem that you're solving. You will know how to apply the equation in number 2. I'll show you when we're doing probably in the trusses later on how number 2 really comes out. So it is telling you have to look at your frame, and out of experience you know when to apply which equilibrium equation. That's what that one is saying. And this number 3 now, if the answer for the unknown comes out as negative, right, which you will see in a lot of the problem that will work, it means that the assumed direction is not correct. It's reverse, right? So if you have, for example, if you assume that the body is in tension, but the body is in compression, the sign is minus, then it says it's a compressive force rather than a tensive force. Tensive forces are positive, right? All right, let's move along. So for this problem there now, the weight of a boom is 120. So the boom is lifting up this crate here, and the center mass is right here, and the load is 600 pounds. So this is 600 pounds being lifted up. You have support reaction at A, B, those are some. These you know that there's a reaction going into here. You know that there's a load coming down here and there's a weight coming down here, which is 600. And then you want to find the reaction at these 2 points. So first of all, you're going to establish X and Y coordinate. You're going to determine if there are any two force member, right? Then you're going to draw a complete free body diagram of the boom and apply your equilibrium equation. Let's look how this is done. So here now we see that the reaction is going into B here. At A, there is a point here. Let's go back to this point. It says you're going to determine if there are any two force members. So two force member, where's the two force members? This beam here is a two force member. So two force, one in the horizontal, one in the X. So here now we look at the distance. The distance between here is 1. This is 3. But also the distance coming down here is 1. And this is 3. This is 5. The 120 comes down here. That's the center of gravity. And the weight of the stuff is here. Right? This is labeled FB, which is unknown. AX is unknown, and AY. So we're going to look now to see how we can solve it. So in this system here, right, we continue. This is a frame that you have. You have a free body diagram of a boom, and its system is in equilibrium. So we're going to apply our equilibrium equation about the point A. Wherever you apply your equilibrium equation, your AX and AY is nullified. It's not in your problem anymore, right? So all of that is not in your problem, right? And so when you take the moment at A, let's go ahead and take the moment at A now. How did we get? So firstly, let's look at external forces that we have. 125 pound, 600 pound, right? This is A, B, G, and D. They didn't bother put C. All right, so let's look at it. So the 120 from A, and I'm gonna draw now. So this is a point where you're taking all of the moment right here. Everybody see where I'm taking it? Hello, everybody see where I'm taking it from? Can somebody acknowledge,
Yes,
please?
sir.
And then now there's a distance from here so to that to G. This is a distance, and G is a sliding vector coming sliding this way, so it makes a right angle there. The fact that it's there, we assume that clockwise, anti-clockwise is positive, so clockwise is minus. So it's going to be turn the body that way, right? And how do you know that? Because when it come down, if you spin with it, it's going to spin this way. It can't spin the other way, you know. So it's like on a swing song. You know, you sit on it, and depends on where you sit, it's going to move with you in a particular way. So if you sit at the end to the left, and you are the only person on it, it's gonna come down and go anti-clockwise. And if you sit on the other side, so it's similar. So just think about it. Right? When you're small and you sit at some swing song or whatever, some balance thing, you go to the circus and you sit on it, whatever. All right, so now it moves, and it's minus 125 times 4. Done. 1 plus 3 give you 4 for that distance. The next one also, you see that the 600 is going to be doing the same thing. What is distance from A? It's totally distance is going down to be 9, and it's coming down also. So therefore, that is 600 times 9. What about this force down here? This force will have a component here. It will have one here. So it will have two components, one in the X and one in the Y. So that's Y and one in the X. So the one in the X, this one they have now is what? Is a vertical one. So the one in the Y, right, is going to be FB sine 40. Because you can clearly see that the opposite side is going to be sine 40. And what's it perpendicular distance now from A? So if you go up here, it will be sliding vector slide to this point. So obviously the distance from here to here is what? 1. And that force is going to be doing that to this body. Turning it into the what you call it now? Counterclockwise, which is positive. And similar, the other component, when it is here, coming all the way here like a sliding vector, its distance from A is what? 1. So where is it going to turn the body? It is definitely going to turn the body that way. So it's going to be turn the body, and it's FB cos 45 times 1 equal to 0. And so you'll get that. After you have done that now, you find FB. So you're going to apply your regular equilibrium equation. Some of the forces in the X. So let's look for all the forces in the X. So we have 1 here. You have the component of FB right here. Right? So those are only 2. So you put, and then you had found FB. So you put FB component here. And this is the only unknown. So automatically, AX is going to be minus 3,210 pounds. What about FY? If I was to clean up this a little bit, it's a little bit messy. If I was to clean it up. So for this one, all right, what is happening here now? Let's go for a right again. Right, we get this. All right, and so for this one, look for all the forces in the vertical. So you have 1 here. You have the component that is going up here, which is sine, which is FB sine 40. And then you have this one and this one. So you simply add them together. So you have a positive AY. The other component going up is positive, and you have these two coming down at negative. And simply you can transpose AY. All right? Simple as that. All right. So here now you have another system, right? Not sure I'll be able to go through all of this. I'm gonna quickly just scan through. So you have a load on the bend rod is supported by a smooth inclined surface at B and a collar at A. the collar is free to slide over the fixed incline rod and the support reaction at A and B. So you're going to establish that your X and Y again, draw your free body diagram and apply your equilibrium equation. So the first thing you have to do is draw the force. So here you draw the force. One force is going in here. You have a moment here, which they tell you, and they tell you it is what? 200 and something pound. That was it there, it was given. All right. And then you have one coming down and one going inside here. So this is one member that is unknown, another member down here unknown. So you have two. And so you have drawn your free body diagram and you have established that your right angle triangle here you have, it is a 5, 4, 3 going into this one here. Similar, this is not a 5, 4, 3, this is a 5, 12, 13 triangle. Remember I was telling you about them? So this is one. Giving you force, it have direction, magnitude and direction. And so you can see all of the different dimensions here, right? And so you just jump around quickly and you're going to find the forces in the sum all the forces in the X. So you start with this one, which is going to be cos is 4/5 times NF, NA, and you get this one. And similar for this one, it's 5/13 for the cos, which is the horizontal component, and you simply put that in. So you get the equation 1 here, right? Similarly for the Fy, you're going to look for a component here. You have one which is 12/13 for this one, see here, NB, and this one is 3/5 NA. And simply you form two equations and you go ahead now and you solve them, because what you do, you transpose a one, put it in the other. Everybody remember how to solve simultaneous equation, and you go ahead and you solve these, right? Simple, just you have to first, the challenge is, do you know how to put these reactions and where to put them? Those are what the notes before was telling you, that this is what you have here. This is a color, so it will just have one reaction here, simple. And then this is another point here that's resting on rod. So another perpendicular. So they all are right angle to these here, right? So you can quickly see it, right? And you can see how they came about to this. If you have this triangle across here, then these alternate angles here. So that is alpha, and then you can simply work it out. So you can look at that in your time. What about the taking moments now? If you take the sum of the moment at A, because this is unknown, to find that, so MA is gonna be equal. So now when you're taking moment at A, very important here, taking moment here, you must remember that you have a moment here that is not accounted for. You can cancel it out here. Please remember that. So all you do, take your moment at A, which is right here. You will have to remember to put in this one. So you have a positive. I'll look the direction that it is going. It is going in the anti-clockwise, which you assume is positive. So if you look carefully at this diagram, you will not see it here, but we know we have a moment. Remember, we'll show you these colors, that the color always have a moment there. So this is going in the anti-clock, which is positive. And so you have to put it back in your equation. So if you see a moment on your frame, please put it back in and add it to the other moments. That's how you solve it. So for the 100 coming down, taking moment at A, it's going to be 100 times 3, but it is going in the what? Clockwise direction, because it will swing in the body in this direction for the 100. What about what other thing we have there? So we have the 200. So another moment is there, and it is going what? Clockwise, so it's minus, and then we can take the moment, the components here now. What about the component down here? So remember now, NB is not in the expression. Why? Because it is out. Because you're taking moment there. But the moment, this other moment hanging there is in effect. So remember those things. So this has two components here. It has one going here, and it has one coming here. So it's two it have. So look carefully now. So one is going up, and the distance from here is what? 6. So the component, which is what now? The vertical component, 12/13, right? Times 6, see down here. And the one that is going here, and this is like sliding vector, coming down here, and its distance from here is what? 2. So it is sliding all the way through here, and it is going to turn the body in a what? Clockwise direction. So it is minus. See there? And so you just simply add both of those, and you will have first of all, we found these before, so you can substitute those values in, and then you find MA from that. It's as simple as that. Not difficult at all, right? Once you know what to do and you follow the principle. And so the steps here you look at, steps are solving 3D equilibrium problem. If not given, you establish some suitable X, Y, and Z coordinate system. So for the 3D frame, draw a free body diagram again, apply the 3 equilibrium equation, and note two forces of equilibrium equation coordinates of the two axes of the plane, and one moment about the third perpendicular axis. You remember when I told you that whenever you have the force arm and the force in one plane, the moment is in the plane perpendicular to it. That's what number 3 is explaining. Number 4 is saying oftentimes 3D solutions are simple, but students need to see the best coordinate, and then you apply the equilibrium equation to start. So remember, those are very instructive comments. And see them here again. So this is talking about one unknown. So we're just showing them again on a surface. You see that you have a reaction here, cable, reaction going out, roller. How many forces in the roller? Typically once it's rolling, one force, one unknown. So you see one unknown. Remember those. For this one, there's a ball and socket joint. It has 3 reactions in all of the planes. Remember that, ball and socket. What about a single journal bearing? It has 2 reactions in the direction opposite to where it can roll. So it can spin through this. So it will not have any in this axis. Let's say that is the Y. It won't have any, but it will have one in the X and one in the Z. And similarly, it will have a moment in these here. So you notice it won't have anything in this. And this is what? 4 unknown. Reaction of 2 force and 2 coupling component which acts perpendicular to the shaft. What about this one? This is a square, not a shaft again. Square shaft is a square beam. So it's a single journal bearing with square shaft. So it's a shaft, but it's a square shaft. This is a round shaft. This is a cylindrical shaft. That's what I should have said. And so you have 5 unknown. Look at this one carefully. So you'll have a moment in this direction only, no reaction. And see a moment there. You have a reaction in the other 2, X and Y. So in the Y, you only have a moment. You have moment in the others, and you have reaction. So that's how you get the 5. Let's jump on. So 5 unknown, 2 force, and 3 coupled. Right? What about this one here? Single truss bearings. Truss bearings, you have 2 reactions similarly, but in this one, you will have a reaction for the truss bearing in the center. Look at that. 5 unknown, right? 3 forces, 2 coupling moment. You won't have any moment there, but you'll have that. So you have to look on the different problem for the type of whatever I tell you, you have at the joint. Whether it's a truss bearings, a journal bearings, and all of those. So single smooth, look at this one now. So you have a pin. You have what? 3 reactions there. In one, you'll have 2 of them, you'll have a moment. But look, this it can move. It can move in which plane? It can pretty much move more in the Y. You get a reaction there. You get a moment there. But in the X, it cannot move. There's no moment in the X. So you only have a reaction because it is spin here. And that's our 3D. So that is moving up the pin. Single smooth pin in the 3D will have 3 reactions. So how many forces we have unknown? 5 still. 2 moment and 5 forces in all directions for a 3D pin joint. What about an inch now? An inch will have all 3, but in the direction that you can, where the inches is going, they will have no moment, but you'll have a reaction. So it spins, it can spin between from the Z to the X, but what will happen there is a shaft spinning. So in the Y, you'll only have a reaction, but no moment, right? So you'll get a moment in the X and a moment in the Z. 5 unknown. This one now is spin in 3D. So it's a fixed support, fixed, I wouldn't say pin, it's fixed support. So it's like a cantilever, but it's fixed support. Reaction in all three, moment in all three. 6 unknown. So note those, please. All right. Now, I will not look on this one. I'm going to skip over this until we come back to this problem, right? So I'm going to skip that and we'll go back to the other one. Where far we are now? We can do another 20 minutes on these. So let me get to the other one that we were doing before. And I left it, yeah, I think this is it. So this one here now, what you need to understand with these topics is pretty much trying to finish it this week, right? And then next week we see we can sift through it, but we don't have the time to spend all of 2 weeks on this topic. It's long, all right, but you're gonna have to read some of it. Material overlap, so recognize that, please. And it is just emphasizing, but we don't have the time. But you can read it. Please spend some time and read these, right? So look at it now. 3D free body diagram, equilibrium equation, constraint, and statical determinant. So these are statical determinants. It's not statically indeterminate where you don't have the amount of equation to solve it. Statical equation, right? But it is constraint. All right, so we're gonna look at it. You can see that these are heavy equipment. And we're looking at the joints that is fitting. We're gonna look at application. So look at this one now. You have a joint here. Let's say that this is a crane or something, heavy lifting machine. It could even be a crane, it could be a tractor, whatever. But you have a ball and socket joint. Journal bearings are often used in mechanical system. To what? To design the joints or bearings, and the support reaction at these joints and the load must be determined. So you look careful at them. Now, let me go to slideshow, as I'm not into slideshow. All right. Then now, here now you have, this is a tie rod from A. So you look now, you see that sometimes you see these in buildings, you see these sections that you have here, these covering here, but something will need to support it. You don't want it tear off from here, maybe to wind and whatever, and it's not sturdy enough. So it is anchored by a cable here at A, something is anchored at C, something at B down there, right? All right. So, and you have the wall at D. So let's look at it. So say if tie rod from point A is used to support the overhang of the entrance of the building, it is pin connected to the wall at A and to the center of the overhang at B. If A is moved to a lower position, right, D down here, will the force in the rod change or remain the same? By making such a change without understanding if there is a change in the force, failure might occur. Of course it will, because it's going to require a different force up here from this. You can't just change it, and so if you do that, and even if you have this up here, maybe you need another one balanced over here, and you're going to need more down here because the load, the strength of this material, when it becomes smaller, you're going to hold a smaller load. So that even from those common sense perspective would tell you. So the amount of tension half of this can support, it probably 2 times it is supporting now. Look at it if it's not practical. Do we agree? Anyone? Hello? Are you guys with me?
Okay.
Yeah, man. So it is practical. So you can relate to it. So look at this 3D equilibrium problem. If not given, establish a suitable XY coordinate system, right? You're going to draw your free body diagram again. You're going to apply your equilibrium equation. And remember, we talk about the 2D axis plane plus one moment equation, give it the third perpendicular axis. So we're going to look at all of that. And often a 3D solution can simply are simple, but students need to do the best, look at the best coordinate systems. Now look at this. Remember we spoke about this in unit 6. So reminding you again. So look, this is this is a Z, this is a X, this is Y. What is this saying here? So force in the 2D for XZ, where's XZ? XZ up here must cause rotation in which axis? Must be this one, the Y. If you have your moment arm and your force in this plane, which is blue here, force in the 2D, which is going to be what? YZ, must cause rotation in only the axis that is perpendicular to it, which is, of course, be X. And similar, if you have your moment arm in this plane, which is your XY plane, then you know that your rotation must take place in your Z axis. So what we're saying, the axis that you are having your moment arm in your force time distance, there is a perpendicular, the axis that is perpendicular to it, you will have your rotation taking place there. So force parallel to an axis cannot cause rotation about that axis, right? So if it is parallel, so if, for example, if you have a force parallel to here, it can't necessarily cause rotation in this axis. And similar, if you have a force parallel over here, it can't cause rotation in the y-axis, right? That's what we are simply saying to you. If you have a force in the x up here parallel to the y, to the z, it cannot cause rotation around the z. If you have one parallel to it over here, no rotation in the z again. And wherever it's parallel, you get no rotation in that particular axis, right? All right, look at this system here. So this is more like a this is holding up something, right? So it's a little crane. It's a small crane, which weighs 350 pounds and is supported on oil drum. All right, whatever purpose. How do you determine the largest oil drum weight that the crane can support without overturning? And they say what roller reaction is impacted at the point of overturning. Anybody want to answer those? So you have G, where the center of gravity is. There you can see the point is labeled there, right, where center of gravity is. So that is going to be dependent on a lot of factors. Let us continue on. Right. So now where G is, you see a weight coming down here. There's a reaction at each one of the wheel. This is supposed to be over here, shift. Right? Don't worry, it's supposed to be right at the B. This is right at C, right? So you're going to derive some of the forces in the X, some of the forces in the Y, some of the forces in the Z, and similar the moment, some of the moment in each of the axes. All right, let's look at how that is done. So similar, we go back to these same principle. You have a smooth support, one reaction. You have a ball and socket, 3 reaction. Journal bearings, you have how many reactions here? You have 2. There's none in this direction where it can roll. Remember, it can roll in the Y, so there's none going to be in the X and the Z. And those directions that it doesn't roll in will have a moment. For a inch, these are, you'll have 3 reactions but only 2 moments. So 5 unknown here, 5 unknown, 1 unknown, 3 unknown, right? So a few examples are shown above. Other support reactions are discussed later. As in general, if the support prevents translation, which prevents it from moving in a given direction, then the reaction force acting on opposite direction is developed on the body. Similarly, the rotation is prevented. A coupling moment exert on the body by the support, right? So we establish all of that, and we remember these again. One unknown, one unknown. So we had done all of those before, and we're just gonna jump on, right? So we had done all of those. So I think we had looked at these now. So here now we have some important notes. You have, this is constraint here and here with different bearings here and another bearings here, but a load is here, so you can see it. And then similarly, you can see one is constraint here. There's a force hanging here, and there's a cable here. So there are different type of systems here. Look at these below. Below now show you the different reactions. So for the journal bearings, 2. Look good. For this one, none in the direction along the pipe, but in the perpendicular direction, right? So you see they have established a Z, Y, and this is, of course, your X. So the X not labeled there. Don't know why the label drop off. So all these forces, you see, you put out all the forces here, so you're able to identify that. What about this system here? So here we have, it is spin here. So we know we have a moment, at least two, but in one direction where it can roll. So in the Y, you only have one reaction, but you don't have any moment. You see that? Because the type of bearings that you have. Right? So you look around here. Right? See them? Single truss bearings. You see the single truss bearings there? All right, so you have to remember all of these so for example, let's say you have a truss bearing there, that's all you'll have these reactions going there. How many reactions you have? 3, and then the moments here. And similarly, you have these bearings here, so you know that these is the journal bearings, so you have 2 reactions alone with the journal bearings. All right, perpendicular to the direction that it doesn't roll. What about this system here? So you have another journal bearings here, 2 reaction here. This is a inch, so you notice it have 3 reactions. And then you look at all the forces, then you have a support here. Simple, this is like a roller, so 1 support. So if you see them, so single bearings or inch can prevent rotation by providing a resistant coupling moment. However, it is usually preferred to use 2 or more popular aligned bearings or inches. Thus, in these cases, only force reactions are generated and there are no moment reaction created. Right? So you'll say this is only force reactions. All right. So in these cases. So look, you apply your equilibrium equation. 2 vector equation can be written in 3D. So you can write the sum of the forces of X equals sum of forces in X equals sum of forces in Z. So all of that. And similarly, you could write this one. Right? For these equilibrium systems. The moment equation can be determined about any point, usually choosing the point where the maximum number of unknown forces are present. So you're going to simplify the solution. Any force occurring at the point where the members are taken do not appear in the moment equation. So you're going to see what we're talking about now, Charlie. So look at this system again. So you have one reaction here. It is pinned up here. So anytime it is pinned up here, you have reaction in all different directions, right? And you have moment in all different directions. That's B. What about here? This is a simple journal bearing, so it's only what? 2. Then you have reaction here, reaction there, just as you had them there. So they are redundant constraint. When a body has more support than necessary to hold it in equilibrium, it becomes statically indeterminate, which we explained to you before. Problem that is statically indeterminate has more unknown than equation of equilibrium. Are statically indeterminate structure used in practice? So I told you the answer for that. Yeah, we do. Do you use them? All right. What about this? Right. Improper constraints. So you have 2 joints here. These are what? What type of joints are these? Anybody can tell me without looking? What type of joints you see here? What type of joints you think these are? Based on, what's that?
Ballpoint.
No. Anybody else want to try? One more person try. It's a ball something. You said ballpoint?
That's what she said, sir. Ball joint.
Yeah, she's close. It's a ball and socket joint. Yeah. So she's close. All right. So if you notice, look over there on the free body diagram. You see that you have reaction in all the different directions, as we had said on the template. And all of them have reaction in all of the different areas. While we have 6 unknown, there is nothing restricting rotation about the AX axis. Right. In some cases, there may be many unknown reactions. So if you look at what is happening over here with these beam down here now, you have A where you have the pin joint and you have a roller at B. All right. So you have P. You can see at A you have 2 reactions. And at B you only have 1 going. So it will normally, you have a reaction. And the reaction is going to be perpendicular to the direction that you can roll. So you can see the reaction drawn here. So it says the sum of the moment at A is not equals to 0. So if the support are not properly constrained, the body may become unstable for some loading case. So this is typically an unstable loading situation, right? Jump along here. Let's look at this problem here now. So now we see we have some bearings here. So the rod supported by the truss bearings. So this is a truss bearings. And what you know about truss bearings is they have reactions in almost all of the different direction, right? Right? At A, and a cable at where now? BC is supported on 80-pound force. The reaction at the truss bearings A and the cable B. Let's look at all the reactions now. So use the established X and Y plane, free body diagram, and equilibrium equation. I will jump on and look at it. So in A, we can see that clearly there is, and you see, how you rotate. This is a positive way to rotate about the X. Positive way to rotate about the Y. How do we determine the rotation, guys? How do we determine rotation? We determine the rotation by what? Anybody know? By the what? Isn't the right hand grip rule? Remember that? Right. So there's one direction that you're not seeing any reaction there because it can rotate in that where it says actually 2, so it's AX, AY, yeah? And so it can rotate about. So it will rotate about in the Y because it can move in the Y. So I'm getting a reaction there, right? It didn't say it's a truss bearing, so it's a journal bearings. All right. So apply the scale. So you have to know the type of bearing. Apply the scalar equation of equilibrium appropriate order. So the first thing we do, we draw our free body diagram. So if you notice the force here, the 180 is placed here. The cable is here, and so the direction from here is going up into the where it is anchor. So see it here. Note the direction of these forces. So let's look at them individually. So you're gonna apply your scalar equation of equilibrium in the appropriate order. So we get some of the forces in the X. So look in the X now. Where's the X direction? So some of the forces in the X here. So you have what? You have an AX here. But is there any other force in the X? Look good. Is there any other field in the frame? Equal to 0. There's no other force in the X. What about in the Z now? In the Z, how many forces we have? We have several forces. We have one going up, another one going up here, and one coming down. So some of the forces in the Z, you have AX in the positive direction. You have the 80 coming down in the negative, and FB going up in the positive. So see here, just like that. So we have two unknowns, yes. So we have first equation there. You get one equation there now, then you need to go to another moment. Now you're taking moment, you're looking for the moment around the Y. So many moments around the Y now, right? Let's look at the moment around the Y. And so you have to be careful now, guys. Concentrate with me now. So we're gonna sum all our forces in the Y direction. So I already see the Y is coming this direction. Now, what did we tell you about the Y? In order for you to have moment around the Y axis, which is this, which plane should we be looking for them in? They cannot be in the Y. So they're clearly, which plane do you get a moment in the Y? Can anybody look and tell me? Which plane? Identify the plane for me.
XZ.
XZ. So possibly this one. So if you look at now, you see that you have two forces in the XZ plane. So some force here in the Z. These are in the Z. So therefore, it's going to be a distance. So if you were to map these to over here, tap over here, just bring them over here to show you. So you'll have one coming down here. I have another one going up here. All right? So that now you can find moment. So the moment now for the 80, let's look at the 80. What's the distance from the 80 is 1.5. So you have what? You have a perpendicular distance. So you have a force and your perpendicular distance. So you see it is 1.5 times the force, and it's going down in that direction down there. Where is it going to turn it around the y? Remember the y, it is, so this way is positive. If it's going to turn it in the opposite direction, remember this is the axis, the turning axis. If it is going to turn it, if it come down here, I'm going to turn it from this distance, and it's going to turn it in the opposite direction of this, then it is negative. So see it here, negative. Body follow that? So in other words, it is turning the body this way rather than turning it that way. So it is going that way. Can you see that? Everybody can see that it's turning in the opposite direction? Yes or no? Everybody see that? You see that it's turning in the opposite direction?
No, sir, when I get that. When I get that, sir, go over that.
So I want you to, yeah, my acknowledge that you don't get it. Let me go again. So look, this same force here, the distance from here, let me draw it over here. It's there over here, so it's the effect. See there? It's coming down here. It makes right angle there. You see it now? It's acting from this axis. So this is a pivot point, and it is coming down here. It's going to spin in the body in the clockwise direction. You could consider it clockwise, but how we really say it is your right hand grip rule tell you that when you close your fist in the and put the thumb in the Y direction, you must look the direction where your finger is going, the sense of your finger. Where be the sense of your finger going? It will going more into what you would call the counterclockwise. That's all. When you put your finger to that one, just consider it. Put your finger to that one, close your hand, and you'll see that this is going. So if you look now, it's going opposite to where your fingers would be going. And so you know that it is going in the counterclockwise, which is minus. Right? You got that now? It makes sense?
A little bit.
So look, let me tell you. So if I was to get a different color, let me get a different color. Maybe that might help. So the body is here. This is a force. It's blue. It's coming down, right? And then this is a right angle. This is your 1.5, and this is your force here. This is your 80. So when it curve, it going curve the body that way. It coming underneath the Y rather than over the Y. This is your pivot point, you know. You see it? Look at it in the 3D frame, guys. Look at it. So it is in the Z, right? And this is in the X. So it's so what you have in here is this. This is simple what you have here now, guys. This is what is going on. So this is 80, and this is a 1.5. That is a right angle. So this is a force. This is a pivot point up here. You see it now? So it must turn it that way. This is the what? This is the ZX plane. You see it? You see it, guys?
Yes, sir. Yeah,
it's spinning around here, but it's spinning in the opposite direction to where it's considered positive. Right? Remember what the right hand grip rule shows in a right hand grip rule too. If you close your finger and put it in towards the Z, in the same direction that we have the pipe here, close your right hand, put it towards the Z, your big thumb towards the positive Y, and look which direction your finger is going. That will give you your positive direction in your finger all sense. If it is going opposite to that direction, you know it's going opposite way. And I'm done. All right. What about the next one now? FB. FBC is going up. And then you have your perpendicular distance here. What's the distance going right across? It is, let me clear up that. This is messy. So it is all of that. Can you see the distance now? All right. What's the distance? So the distance is 3. So this distance is 3 from the pivot. The pivot is here, and this maps out. So this is your Z, this is your X distance. So to get your force going here, So this is where you have your rotation. Your rotation is going to be in that direction. So this is going to be turning the body around this way now, in the positive way. So it's going to be turning the body that way, right? And if it was the regular 2D, we'd say that it is anti-clockwise, eh? But you have to use your finger for this one, your right hand grip. So it's going around the Z, so it's coming this way, which is positive. You see that? So therefore, this is FB times 3 equal to 0. And then you just go now and equate that to 0 and solve for FB. So FB is 40 and AZ is you got that? I hope you all clear with that. And I'm running on. All right. And then now it says here, now we write the scalar moment equation about what point axis. Right? So point A, x-axis and Z. So now let's look for the moment about the x-axis. Now let's look at the x-axis now. So let's look for your moment around the x-axis. You do the similar thing like what you did for the y. So now the first thing you know that there is a moment here accounted for in the x-axis. That see here, this guy here. That one has a moment, so you have to put it back in the equation. Then we're gonna look at the different forces. So in order for you to have a rotation in the x, which plane are we supposed to be focusing on for your moment arm?
The YZ.
So you're supposed to have a plane over here, which is supposed to be your y, z, right? So right, and so the force must be in this plane for you to get rotation in this axis. Right? Let me draw it somewhere clearer. So this is it. This is it. Your moment arm, your force is here. If you have force over here, so you have two forces and they're in the Z, and you have your moment arm in the Y, you can get rotation in this axis. Right? Whether positive or negative. Right? So that is a right angle. All right, I hope you follow that. So this is the X, this is a Z, and this is a Y. And this is a plane that you'll have the moment arm. All right, so now we go through, let's look at it. So you have the 40. So the 40 is in the Z, right? So it's going to be 40, right? All right, so you have 40 here, 40 times 6. Can you see the 40 times 6? So see the 40 going up here now. You see it here? This is the 40 that you must concentrate on. So this 40 is going to be coming, it's going to be acting in this plane, and this is the distance. So 6 times, so this is it. So it's going to be turning the body more like around in the positive way. Right. So it's going to be acting that way, and its pivot point is going to be here. Right? So it's almost like 2D in 3D. So this is the right angle. So you're going to spin it. So it's spinning it up there now. So see it there? So you're going to spin it around based on its effect. So the distance is 6 here in the Y, and the force is in the Z. So that, if you look carefully, that is one of them, and that is positive. What about the 80? The 80 is not positive, but it's going to be doing the same thing at a different distance. Same 6, but it's going to be turning the body in this way. So it's going to be turning the body that way. It's still going to be have the effect here. So its plane is right here. See its plane there? This is right angle to the X. So see it plane there. So the force is there, the distance here. So it makes right angle to that axis there. Or maybe you want to see it down. I don't know what best you want to see it. Maybe you want to see the force coming down, and you see the distance here. See the distance there, and the right angle is down here if you want to see it better that way. So it's going to be turning it in the opposite direction. So therefore it must be minus equals 0, and then you solve for that MA that you don't know, which is 240. And for the Z now, let me clear up that. For the Z, Let's look for that. Come again. So for the Z, where's the Z? So the Z here, which plane will normally have the moment arm in? The force and the moment arm in for it to get rotation. Remember we have been talking about that? Which plane do you get? You have to have for it to get rotation in the Z axis. Which plane do we operate in? Hello, which plane? Which plane?
XY.
XY. So it must be in this plane down here. Alright? So force and moment arm must be down here. So let's look for them. So we see a distance down here. Do we have a force down here? Is there a force down here? There's a distance down here, but is there a force? So there's no force down here, so it is 0. So MZ is 0. But there's none. Alright? Alright. Next one, same treatment. Alright. Not a problem. Same problem. We're going around some of the moment now. So we can operate. Those is a 2D approach. Let's look at this now. So we're gonna sum the moment at A. Right? Let's see how this go. So you're gonna sum the moment at A. And in order to sum the moment at A, we're gonna use it the 3D metrics approach. So you're gonna look for your position vector of RAD. Where's RAD? RAD is going to be to get the moment about A, you have to be stretching and going from A to B, right? Right? So you must touch a force. So we touch a force. Two forces are there, you're touching both of them. So one you're going to touch a 40 force, and one you must touch the 40. Remember, I told you that when you have a point, and you have a force, you need to get a position vector that touch the force. So if you have a point A here, and you want to get the moment about some force, if it's the 80 force, it must have something touching it. And so it's supposed to touch it at B for that one, and it touch D for the 80. For the 80, touch it at D, sorry. And then for the BC, touch it at B. So you have a force, so you're tucking it around A. You have a force there. So you know it will form, so you need your position vector, which is AD in that case. So AD would have been, where is it? Come on. Right, so your AD is here. So this one is your AD, and that one is your AB. So you always need a line to touch from point to the force. From the point that you find it to the force. So you find it about A, but it's two forces over here from A and give it to you. So you have that one and you have that one. And then similar, you have some moment. You have a moment here, both AX and AB. So you had them. Here, you have that one there and that one. So you have them into the equation because you can't leave the moments them hanging. And so you would put in the coordinates for D, which is going to be what now? Minus 1.5 X, and you have 6 for the Y, and the Z is 0. See there? And then the force is going to be what? Using the unit vector, in the Z is going to be 0, 0, minus 80 because it's going down. And similar for this one, it's going to be 0, 0, 40 because it's going up for the 40. What about you get the position vector of AB, which is B minus A. So you have to solve. Once you get the position vector of B, you already have AB because A is 0, or is the origin. So it is going to be, X is going to be what? Minus 3. See it there? Y is going to be 6. And Z is going to be 0. And you simply have your two matrix. And you go ahead and you find these values here. But remember how to multiply that. You multiply them out, you get the different values, and then you add these two in it. All right. Those are two unknowns and equal to 0. So here you have these two equals to that expression there. All right. Right. All right. Everybody saw that? Everybody all right with that? Nobody lost there? It's straightforward, right? Any question there? Pardon me? Nobody good. All right. You said you're good, right? All right. So, all right. What time we have now, guys? Okay. We're going to wrap up here. All right. Well, let's go one more and then we'll wrap up. This one is kind of long. All right. Next week, I'll continue. I'll touch on the other topic. I'll have to pinch a little bit to finish this topic. When we finish this topic, then I'll go over to share. So I'll leave it for here. I could probably wrap up the last one here. All right, so for this one, let's say we look at this one quickly. So this one is the same thing. You have a 500 force. So the platform, the uniform plate has a weight of 500, supported by 3 cables. So you have 3 cables here, right? And I give you the dimension. You have 200 force here. Right, let's look at the free body diagram. So let's say in the center, you have the 500 in the center. You have a weight here. So you have 3 forces going up, 2 coming down. Here what you do, you apply the scalar magnitude only equation. So sum up the forces in the Z. So you look for all the forces in the Z and you look for them. TA, TB, and you add them. And what about the others going down? You have 2 going down, so you put them in there. So you get a force in the Z. All right. What about the moment in the X now? Moment in the X. For you to get moment in the X, you have to look in which plane? You have to look in the Z what? The ZY plane. So the ZY plane now, you have the distance here in the Y is 3. You have to look at each force. You have one is 1.5, one is 3. Right, that is one of them. And then what other distance you have there? So those are some. Let's look at them. So you have TA. Oh, I didn't look at the TA. TA is times 3. Right? So TA over here. TA is this distance over here from the X is 3, where the TA is, and it's gonna spin it in the positive direction. So see it there. TC is where now? TC is all the way at the front here. So it's gonna label back is this one at the front. This is also 3 in the positive direction. The other one is a 500 in the middle. It's 1.5. So it's 1.5 times this. It's gonna be negative, right? And then this is going to be also negative, because both of them are going down. What is the distance? This is 3 from X in the XY plane. And so you see them right there. And then now you do MY. Moment in the Y. For you to have moment in the Y, you need to be working in the ZX plane. So you're gonna look for the forces in the ZX plane now. So you look for the distance along in the X and the same forces up here. First one, TB, going up. So that is going to go opposite to the direction, the positive direction. So it's going to be what? 4 times TB, but it's minus, right? If you use the right hand grip rule, you would see that the positive direction is going around here. And so if you look at TB is here, and the distance is out there. So that is 4, right? So it's going to be turning. This is the right angle. You're going to turn the body that way. TC is here. The distance is 4 again. Right angle is here. So it's going to turn the body that way. So it's going to be opposite. And then the 500 is going to be positive. What is the 500 distance? This and the distance from here to out here is what? 2. So it's 2 from the Y. Right angle is formed there. So it's going to be turning the body in the positive direction. And the 200 is here, which is what? 2 from the Y coming down. So it's going to, when it come down, right, it's going to be turning the body also in the positive direction, and it's time 2. So here you can form a system equation, 3 equation, and you pretty much juggle them and solve it. You could work. So you have equation in TAC and all that. You're going to simply try to substitute one in the other and just substitute until you solve them simultaneously. All right? And so you have them there. You have equation 2. you'll use equation 2 and 3, right? You express TA and TB in terms of T, and you'll get that. So you'll end up with that. And then simply you substitute them back into equation 1. So you use these two together. You leave that one. When you get these two now, you substitute all of these values here. So you know what TA is right there, TB is right there. You had them. They're all in these right here. And you just simply solve for TC. When you get for TC, you put it back in here and you simply get it. So it's just as simple as that. All right. Next week, I will go on further and wrap it up. All right. So it's a bit long. All right. All right. So next week, it means that we'll use the time to go through the slides, and if anything, we'll go through we have one tutorial question for this topic also. All right, so now that we are at 7:30, we are gonna go into Truss. I don't want to run out, and I'm gonna get to focus on Truss. All right, so that, guys, has pinch half an hour from your lecture for your from your tutorial for your lecture. So let's jump into your slide that you're gonna next week. We'll go through these. All right. All right, let's jump into your slide for today. This is it. And I did not close out so I'll have to go over it. All right, so this is a question for today. I have another one that is on the site. And I have the solution sheet. If I don't get to go for it, I'll release all the solution sheets to you. Right. I chose to do this one because it's a little bit simpler. You know, I don't have to work the same one over here. I'll give the solution for the other one. All right. So this is a simple one. Let's jump into it. I am going to I didn't save all of this today. It's working. Let me just save it and put it somewhere. And then so this is tutorial for which group? This was Tuesday group. Unit 8. Right. Did I put it here? 26. Always have these recorded. All right. So now I'm going to close out this, and I want a brand new file. All right. So here now we're going to drop this here. Oh, thought I had something to drop here. I'm going to paste this here. All right. Beautiful. All right. So this is a question that we have now, guys. Remember about Truss? We did Truss last week. And I touched on it and said that when I reach here, now we'll come up with pull it together. So this question is a bit long. Right? Don't know how far I'll reach with it. But it should bring the principle out to you. All right. So firstly, we realize that we have a frame with some forces on it. And this is quite long. I try my best to do as much as possible. Now, the question says, you must determine the reaction at the support. So first you look and you see your global forces. You have 4 global forces that you know. You need to draw your free body diagram. So it's long, but I'm gonna sketch the free body diagram as quick as possible. So let's look and sketch it. Will not be drawn to scale, right? In the short time, right? Will not be drawn to scale. I'll try my best, right? As best as I could do English. All right, because I really can't use much time to draw it, right? But must look somewhat proportional. So we don't look too proper, if I can do it. All right, so this is what it looks like. And then it has some other section here. All right. And there's a reason for you to draw the free body diagram. It's always tell you to draw your free body diagram. Not every case to solve them you have to draw a free body diagram, guys. Especially method of well, section. When you're doing method of section, you still have to draw a free body diagram. What have I left out now? I have left out that. I have everything now. All right, and then now we need to put our loads in. And we need to determine. This is a pin joint, so it has two support reaction, one here, one going there. And it also have, this is a roller here. So one support, it can roll horizontally, so it must have a vertical reaction. And then you're gonna label A, B, C, D, E, and F, and of course G. We'll have left out some force. Nobody told me. One here, one here, one here. Uh-oh, that one is really looking bad. I'm rushing it looking.
I can't see what you're drawing, sir.
You don't see anything?
No, just the tutorial photo.
Lord of mercy. Hallelujah. Guys, why you never say something to me? You hear me there draw, I'm not seeing anything. You can't see it now?
Yes, sir.
Alright. Sorry about that. So I'm drawing this thing over. Lord have mercy, man. Let me repeat myself because I am there sailing on. So look, at these points, how did I get these? So right here, I draw back the whole thing, drew it over. But these here, how did I know what to draw at the support there? Because at the support, right? At the support, you have a pin here, says two. One is going positive X, positive Y because of pin joint. So you need to look at the type of joint we give you in the question. It's very important, it's crucial. So that is A. And then you have another one going into the joint here. All right. See it there? So this is going to be AY. I'm not gonna bother call R. Sometime in the past I used to call R, but it may make the problem kind of odious. This is AX and this is GY. This kind of make the problem simpler, eh? Labeling doesn't have to put no reaction. Remember in the past we put reaction all over the place. But we don't have to double it up and put reaction A, reaction B. We just call AY AX. It's the same thing. So this is the stand is 2, 2, 2, 2, 2 for all of those spans. And this is also 2. So you see all of those are 2. I think you add up to what? 12? Something like that. We have left out some reaction here. Let's put them in. One here, one here. Oh no, there's none at D. Who see that? That are putting in an extra force. And please look if I'm making a mistake. Thank you. All right, so let's label them, put them in 4 newtons, and then you have 8 kilonewtons, you have 6 kilonewtons. All right, and this we don't know. So we have 2 unknowns, 3 unknown so far. We need to finish labeling figure. So this is H, I, this is J, K, and this is L. All right. So now that we have drawn that, there's another critical thing that I need to show you, and that you weren't seeing. So let us backtrack a little bit. So when you start doing your problem, guys, you need to understand the geometry of your problem. Critical. So you look at your geometry of the problem, there are a number of things here that your geometry is telling you. It tells you that you have, look for your right angle triangle. You have one here, and you also have one here. Right? And you have all another one over here. You need to understand the geometry so that you know the angle between the angle to the inclination of the element. So you need to know if that what is that angle here, and you need to also know what is this angle here. They are different. And look, you know why I'm not going to use a smaller triangle? Because I don't have the height of it. All right, but guess what I do have? I have the height of the big one, and I have the distance here. So I end up that it is this is a 4, 3, 5 triangle. You see that? So therefore, I know what alpha is. I know from our tricks that alpha is 36.9. Everybody agree? Right? And you can use any one of the sine ratio and get that. So it's either sine 3.5 or cos 4.5 for the cost ratio. Once you see 4 down here, 4.5 will give you is cos, 3.5 will give you the sine ratio, and you just decide. Alright? You don't need to use the angle up top, just use the one of them. More like the one at the horizontal. And you get that. Alright? So you could use some people, I prefer use the angle in these problems rather than the ratio, because the ratio may confuse you if you don't understand it. So you can just work out the angle and work comfortable with the angle rather than the ratio. Some people may get confused with the ratio. All right, so let's move on. Now that you do that, you have put in your reaction forces and you have 2 here, 1 over there. Now you need to apply your equilibrium equations, right? Because you want to find your reactions, right? I have 2 unknown here. I only have 1 over there. If I take my moment at G, I'm only going to knock out GY and I'm left with 2 over here. That's not helping me any at all. It's better I take moment at A. So I will take moment at A. So you're going to take moment. You don't have to write out this. You can just write this. You're going to sum up your moment at A equals to 0. And that is what that means. And then you can proceed. So I'm putting your hand right there at A. And now we're going to look at all the other forces. So AX and AY is out of the problem. Anyway, you take the moment, they're gone totally. And you're only left with what? The 4, the 5, the 8, the 6, and GY. So let's take them systematically one by one. So the first one is 4. Which direction is it turning? The first one turning. All these are going to be turning in one direction. All of these are going to be turning in the clockwise. And this one is going to be turning in the opposite way. So 4 so the convention we're using is anti-clockwise is positive. Remember that. So we're going to the first set now. So it's AY. Sorry, not AY. 4 times the distance, which is minus 4, times the perpendicular distance is 2. Next one is going to be minus 5, perpendicular distance is 4. Next one, perpendicular distance. What's the perpendicular distance of the 8? What's the perpendicular of the 8 kilonewton force?
8 meters.
Yes. And the 146 is what?
10 meters.
And the one for the GY is?
12 meters.
But it is positive because it's going in the opposite direction. So it's going counterclockwise. Equals to 0. And what that works out to be now. So that now works out to be, remind me. So that is what now? Minus 8, minus 20, minus 64, minus 60, equals to 152. So it's minus 152. Everybody should have worked that out already, you know, man. 12
Yes, sir, that's good.
y equals to 0. So that implies that GY is equal to 152 upon 12. And therefore, GY is equal to what, guys? No, don't work it yet. You don't have to work with me. Now get out on the calculator. Because I'm going to ask them for things them.
12.66.
So you can do that. All right. So I'm going to run it as that. All right. Now that I finished that, and I have GY now, I need to go back and find AX and AY. So I'm going to first equilibrium equation I'm going to use. I'm going to sum all of the forces in the X direction equal to 0. Done. All right. Look for the forces in the X direction. How many forces we have in the X direction? Can you see? 1. So AX is equal to 0. That's what we conclude from that. And that's done. Next one. AY. AY now. How many? So we're gonna sum all the forces in
Sir, before you go,
F1Y.
how you get one as the answer for above.
So look, see there, it alone. There's no other horizontal force. Look, well, you can tell me another one. When you find it, you tell me. Here, I'm waiting. Yes, I'm waiting. All right, let's look at all of the forces that we have acting. So we have one now going up, which you don't find it. Team up here. This AY here. So AY is positive. Yeah. And we have how much? We have a -1 coming down, -4. We have a -5 coming down, and we have two others, -8, -6. Everybody see them? So we have one here, 2, 3, 4, and then we have another one going up. So it is plus GY equals 0. Who don't agree with that? All right? So therefore, from that, but we have GY. So it is AY is going to be equal. So when you add all of this, how much you get here? So you get, this is what? Minus 14. Minus 9. So we have what? 23. So it's 23. Bring over the 23. It becomes positive 23 minus GY. GY itself is what? 12.67. So therefore, what is AY now? What is AY?
10.33.
What?
10.33. 10.33.
Yes, 10.33 kilonewton. All right, good. All right, so we're done. All right, so now we have found all the reaction. That is 5 marks. But I drew this should show you that you need to draw your free body diagram. And it's a sketch, not a draw here, guys. When I say draw, don't misunderstand it. It's really a sketch. All right? So now you've done an artwork inside the exam. Let's clean up this and we're going to reuse it. All right. So I'm going to borrow back this figure and we're going to do another sheet. Not going to work on the same place. I don't want you complain that I work crowd here and you're not understanding. So I'm going to take it out. Yeah. I know person's complaining. So let me just let's do this again. No, this is not what I need to do. I'm doing it the wrong way. I need to click on it and it should open. Where is it? Select it. Yeah, that's it. And I copy it. I could move it to them. That's gonna borrow it. Let's put it down on another sheet. So that we have this here now. I don't want it too big. I don't want it too small. All right. So now when we have that, and we want this also. Let's erase this. I could probably make this a little bit neater. Kind of look crowded right there. So, all right. Before I move it, let me neat it up. All right. So you see the reaction there and reaction there. All right. You can clearly see the reaction there. So there are two reactions. One going in the joint from either direction. All right. I'm gonna copy this. I'm not gonna draw it again, but just have it to a reference. Just a little reference. All right. So let's put it let's pick up a lot of my space. Yeah, so as a reference. So that was what we had for our thing. Now we need some values. We need GX and GY information. Oh, well, let's just write them on the drawing. So we know one is 12.67 12.67, and this one is 10.33, right? Kilonewtons. Right? Those are what we need to know, right? Because AX is 0. So therefore, we can leave that out. All right. Now, after that, now it says here to use a method of joint R section to determine JK. So we're going to find a number of them, and then we reach to a point, I'm going to use method of section, right, in the last one. So let's look at it. So now you want to do method of joint. We're going to consider, the first joint I'm going to consider joint A. So that's the first one I'm going to consider. So when you consider joint A, let's do it here. This is a joint, and I'm going to draw the joint. The joint that I'm drawing is representing, so this is A, and the force that it is, this is AL. So I'm going to assume that it is in tension. So I'm drawing it that way, so I can actually put an arrow that way. I'm going to draw joint B, so I'm going to put it that way. All right. So this is B. I'm going to call that FAB. All right. And there's another force going in it. All right. And this is AY. AX is 0. You don't have to put it in. I know that this is 36.9. That's what I do know. I also know that AL, this one here has two components. It has one in the X and one in the Y. Right? And this angle is still 36.6. So therefore have two components. FAL cos 36.9. What did I say? 0.6.9. All right. And this one is FAL sine 36.9. So it has two components. All right. From that now, I've established that. So
Excuse me, sir.
What?
Excuse me, sir. How did you determine that it's 36.9?
Remember, we look at the triangle, and based on the geometry of the triangle, we are able to determine that this triangle here, and this one here, and that one give us a 4, 3. Give us a 4, 3, 5 triangle. But the height is 3, A to C, so AC is 4 up to K. So that triangle, so therefore that angle down here must be 36. You remember
So
that?
how did you determine the height is 3? It's just
Yeah, it was given. Was given.
Oh.
We don't assume anything. You have to work with what was given you. So the height out here, so the height of the figure going right across is 3. 3 and only 3. So you have to look at the geometry of the triangle. Right. I appreciate the fact that you asked, because some people wouldn't ask and they are ponder it out. All right. Then now, all right. The fact that you do all of that, we are going to go ahead now and apply our Coulomb equations. Now, if I use some of the Coulomb equation in the X, how many unknowns I'll have? So you look quickly. FAB is unknown. FAL component is unknown. So it is not advantageous to use the X. I'm going to use the Y first. So I'm going to sum all of the forces in the Y equal to 0. All right. That might be a little bit too loud. Let me use a milder one. So let's look at it, and we're taking up as positive. So therefore, the first force is the AY, positive AY. And then the other component that I have going up is this in the positive direction. So I'm going to add them. FAL sine 36.9 equals to 0. Right? That's only 2. And so from that, I know AL though. AY, sorry. AY is 10.33. Now so. Plus FAL sine 36.9 equals to 0. Any questions so far? And so from that, I can simply transpose for FL. So FAL is gonna be equals the 10 point something can come over as minus 10.33 divided by sine 36.9. And how much you get for that? Please, can I get an answer there? I'm waiting. 17.2. 0. That's it? Kilonewton. Yeah, minus 17. All right. So, and you could write that. So this force is clearly telling that it's a compressive force. So you could write 17.2 bracket big C, compressive force, to tell you that it's minus. So the assumed direction is wrong. It is actually going in the joint. Right? It is going in joint A. It is not coming out of the joint. All right. Now that we do that, we are left with one more to solve for. So now we're gonna apply the equation in the X. So we're gonna sum our forces now in f of x equal to 0. And what that gives us now. That one is a little bit longer. It have so I'm gonna write it down here. So you have first one is F A B, this one right here, positive. Then you have another component right here, which is going to be F A L cos 36.9 equals to 0. Now we have FAL already, so we just substitute that value. It says FAB will equal to the minus of FAL cos 36.9. And you drop that in now, minus 17.2 cos of 36.9. And you're supposed to get, how much is that, please? Come, guys. How much is that?
13.75.
13.75. And is it plus or minus?
It would be positive.
It is intention then. So it's assumed direction is correct. It is intention. All right, lovely. Now that we have done that, guys, we can now consider another joint. So in considering another joint, I want to tell you, how is it that I'm going to consider another joint? Which other joint should I consider? Because our objective is to reach up top. We're not going to reach there maybe, so by method of joint, because it's a little long, but I want to go as far as possible to show you. So the next joint that I must take either joint, I must take another joint with just 2 unknown. Which other joint leaving from joint A can have 2 unknown? Can somebody identify the joint for me? Which other joint you think I should take? Look over here, so on the joint, look over right over here. Which other joint?
Would it be JC?
JC, no. I'm going to take joint L. Why? Because I have AL already. All right? So, because I don't want it call you up again, and for you to complain that I confuse you, let me just copy it again. I'm going to copy it, carry it down. Do I have to go all the way down? Because I can't see it, so it makes sense I just get another page. All right, I can't see it. Once I can't see it, I'm not going to use the same page. Because you're not going to see it, I'm not going to see it. All right. What I did work out before, I want those values. So the values that I want is everything that I know so far. So I know, let's document them. So I know that we found the joint inside here, which is A, Y. We found GY. This was what? 12.67 kilonewtons, while this was what? 10.33. We found some other stuff. What else we found up here now? We found F, we found FAL. So FAL, all right, what was its value? 17.2. Was it positive or minus? It was minus. All right, so it was a minus, meaning that it's a compressive force, right? That's what we know. What else we found now? We found AB. And AB, FAB is what? 13 point, what is it? 65? Or is that 65 or 56? 13.75? Was that the correct figure? Anybody remember?
756.
75. Beautiful. It's important. So we'll make mistake if we so this is 75 kilonewton. All right, so far we have ABAL. All right, the next process from that, we are going to consider another joint. So the joint that we are considering, I'm going to draw the joint now. We're going to consider joint. So we're going to first statement, you must say, consider joint L. So everybody knows L you're doing. And then we stick a pin here and we draw it. So that is one. And the other one, AL, is this. All right. So the AL now, it is going in the joint, it's not coming out. If you put it in the joint, you can use it as positive. Remember that here, guys. So this is FAL, and I'm using it as positive 17.2 because I've changed the direction that is going into the joint. I don't join out. But however, F, so this is L, and then I have FLK. I'm going to assume that it's in tension, so I'm drawing it out of the joint. And then I have another one, which is coming down here. All right. And then this is B. So I'm going to write FBL or LB. It doesn't matter. I could write it. Doesn't matter. I'm going to write it. They tend to write it with the letter of the alphabet at times, but I like to write LB. I just write it for LB. It should be really BL. But because it's going down, I just put it that way. Doesn't matter seriously. So we have two unknown here. So I need to use method of drawing to solve this. Now you will realize that each one of these forces will have two components, these inclined force. One will be going here, one will be going there. Likewise, one is going here for this one, and the other one is going here. One is in the X, one is going in the Y. All right? This one is going to, and the angle is what? 36.9 for both of them. So therefore, this one is going to be FLK cos 36.9, while this is FLK sine 36.9, while this is FAL cos 36.9, and this one up here is same FAL sine 36.9. Right? So we have them, all of the forces that we need, we have them. So how do we solve this now? I want to get a lovely block. Now, so firstly, we decide to use, we can't use our moment, we still have to use our equilibrium equation, basic equilibrium equation. So we're going to start over here, just to make sure we have enough space. So we're going to sum all, so we look carefully and we decide whether or what we're going to go X or Y first. I think we just have two forces in the vertical, but do we have any quantities in the vertical? We could actually go, if we go vertical, how many forces we have there? We're going to have two unknown in the vertical. We're going to have FLK, FLB, and we'll have FAB. Don't know if that will help us in the vertical. What about the horizontal? We have one known in the horizontal here and another known. So we're going to go sum up the forces in the X direction equal to 0. So the first force is going to be FAL cos 36.9, and then the next one is going to be plus, same direction, you have FLK cos 36.9. All right, do I have any other? No, equal to 0. I have one of these, so I'm going to substitute in the value. So FLA is 17.2. Remember, we change the direction, so it's not minus anymore. 36.9 plus FLK cos 36.9 equal to 0. Transpose for that, what am I getting here now? So I need to find FLK, which is going to be equals to 17.2 cos 36.9. Let's go up a little bit. Divided by cos 36.9. So mathematically, you see that these are the same quantity. So you're basically seeing that F, you see that is actually equal to 17.2 kilo newtons. So FLK is the same value. All right, that's what we are getting. All right, so we can confirm that. If it is correct, we'll check it. All right. What about the sign? Did we have a sign? Let's check the sign. Did we go one is supposed to be minus, right? Yeah, so this come over, that's supposed to be minus. That's minus, right? Okay, when this should come over, they're both going in the same direction. Look, that. So they're adding here, but one is going to be minus. So that is the value of that one. All right, the next one. The next one now.
Sir,
Yes.
sir, for the 17.2, sir, why you change it to positive when it was in compression, sir?
Because I put it going into the joint here, so right here. If you didn't see it, remember I was explaining. I put it going into the joint.
Yes, sir, but into the joint, sir.
So into the joint, it is. I put it as compressive going into the joint, so I change the sign. When we drew it first, we had put it in tension out of the joint. Look, see it here? We had draw it out of the joint and we assume that it was in tension. But when we calculate it, it was minus. So what I did now, moving forward, don't get confused. So joint L now, I change it. I put it going into the joint and put it as positive. Because it is in the opposite. Remember the notes tell us when you see it going in one direction, it's minus, it means it going in the other direction. And you can, if you put it in the other direction, you better change the sign. If you don't change the sign, then the whole problem is going to be off. So remember that. You hear?
Sir, we change the sign.
If look, I am putting it with join L. So I put it going as compressive force. So look, FLK is a tension force. I draw it as tension. It might be going the opposite way too. But I draw it because I don't know. I'm assuming that it's in tension. When I finish calculating it tell me say it's a compressive too. It's a going at the joint. But I won't know that until I calculate it. All right. So yeah. So that's that. Then now I have.
But, sir, you find the AL, sir, for compressive from the previous one, sir. But in this way, you use it as positive, sir. So that may ask.
Come again?
Sir, for the calculation FAL 17.2, you have it as positive, sir. But the
Yes.
previous one is negative.
Yes, because I changed the sign and put it going into the joint because it is a compressive force. So because we calculate it and it says it's compressive, I have the liberty to put it what it actually is. It is compressive. So I'm going to put it as compressive and make it become and change the sign showing that it's going in compressive. I cannot keep it as minus if I put it in the correct orientation in the problem.
Oh, okay, sir.
You see, if I didn't change the sign, I have to draw it back in tension and work with it as minus. I'll have to put it coming out of the joint, which is erroneous. It's not the right way. Right? It would work out, but it was not the right way. All right. So now I finished that. I am going to do FLB because I didn't find that one. So FLB, sum all the forces in the Y. Now, all of the vertical forces equals 0. So what this one going to give me now, guys? So how many of them we have? We have one coming down. F, L, B. It alone coming down. Everything going up. Plus. So that one is minus, sorry. So that is minus coming down. Then we have, what's the next one we have going up now? Plus F, AL, sine 36.9. Plus the next one up there. So that is 1. Then this one. So it is plus FLK sine 36.9 equals to 0. All right. What we have here, in order to get, where am I now? So we are going to look at it. So we need FLB is going to be equals to the summation of these two. So it is going to be just write them back because I carry that over the other side and I'm going to put FAL sine 36.9 plus FLK sine 36.9. All right. What is FLLA now? What the result is? 17.2 sine 36.9, while FLK is minus 17.2 sine 36.9. What that tells you about FLB? Who realize what it is? What is it? What's the value of it? What? It's a zero force member, so it's 0.
0.
Yeah. FLB is a 0 force member. All right. So it means that, remember when we said that if they are collinear, has no load on this point here, then it's a 0 force. This is a typical one. It has no force here, so it is a 0 force member coming from here. All right. So there, so now we have solved for how many forces? We have solved for 1, 2, 3, 4. So which other giant is a good giant to choose? We are going to choose, in the interest of time, we're going to choose giant B. Because we're still working our way up to these. Right? But we may have to stop and use method of section because in the interest of time. I am going to consider giant B now. So I'm going to take down all the information that I have right here. All right, and I'm going to go again. Let me this. I may have to stop for a second. I may have a little bit of disturbance, so I want to stop for a second.
Or could you scroll back up when you finish for a second, please?
All right, just look on it while I say something to someone. Just hold on a second. I'm gonna stop. Let me pause a little bit. Give me a second. Just look at that while I let me make it a little bit small. Everybody can see it. And I'm gonna pause. Give me a second. All right, guys, ready again for you. All right. So, all right, good to go. I'm rolling on now. All right. So we have that information. What else do I need to carry over now? We need to carry some values. So we know that F, where is it now? We know that, let's make it a little bit bigger. We know that FLB is 0, right? So we found those values. And what we had actually found again, we find something else. We found, is which one we said was 0? Was it the right one we labeled as LK? LK is 17.2. Right. FLK
So
is,
to the FLB.
pardon me?
You can go back to the FLB.
FLB 0.
Oh, sorry, the first FAL. Wouldn't that be negative 17.2 cent? So them both are negative.
FAL, no. It's positive because I changed the sign. Remember, I just explained to you guys that because we assume that it was intention. Where did we? We assume that's tension right here. But I went. Did I stop my recording? Did I check it? I'm recording, right? Oh yeah, still recording. So look, we go here and I assume that it was intention, but I realize after calculation that the force is in compression. When I'm drawing the second joint, I don't keep it in tension, I keep it in compression. So I put it going into the joint, right, which now make it 17.2. If it was in tension, I'd have to draw the arrow going the other way and keep the sign as minus. But that's not it. So it's correct now. It's in its right direction and its right value. So you have to be mindful of those little nuances. All right? So that's the only little nuances that you have to be careful of. That's one of them. So we have those. We have A, B, and we have all of those values. So we are going to now consider another joint. The other joint that we are going to consider, which other giant? I was asking you to tell me which giant I should consider, but nobody answered me. So I have to choose a giant off of my own because nobody working with me. All right, the fact is, what you do here, if you look carefully, you will see that giant B, you have all the members of giant B except 2. Giant B has how many giants? It's supposed to have 4 members. One is 0. You have AB, and you're only left with BK and BC. So therefore, I can now consider another giant. So I'm going to consider giant B. And so I'm going to draw giant B. The only problem I have, let me do this and draw it first, and then I'll move down. So I'm going to draw it now. So watch this now with giant B. As also it's going to be a tricky one. I'm going to draw giant B. So I'm going to make an assumption for BK. BK, I have it. Now the force that was coming down in giant B, this is 0. The one what was here, this one is 0, so I can leave it out. You remember that one? LB, 0. But I can put in now BC that I don't know. So this is now going to be B. So this is going to be C. So this is known as FBC, while this is known as FBK, right? And so this giant is coming down here, right? That is coming down there. And then you have another force, AB. You remember what the value was AB? AB was what? 13.75. And it is what? What type of force is AB? What other type of force is AB, guys? You remember?
Tension.
Yes. So therefore, I have to draw it going where now? Do I draw it left or right of X in the X direction?
To the right.
No. You can't draw to the right if it's going to be in tension into the joint. I have to draw it coming out of the joint in a what? Tensive manner. So it is now, this is now FBA. Or if you could still call it, yeah, I just change the label around. It's still AB. But it's just, I'll write it that way to show you that it changed direction. Change direction, so it's now, that is the value. What is the value? The value was what? 13 point, but it's going in the negative. 13 point, what is the value again? 13 something, 13.575, right? But it's going in the negative direction. So if you're using it, you have to use it as negative. All right? It's still AB. So we could still put it as AB, you know, but I didn't want to confuse anybody. Right? So that's why I'm gonna keep it that way for the time. All right, let me just change it. It really matters seriously. All right. All right. So that now we have all of those forces. So these two, all of them, I am assuming that these are in tension. Those are in tension, they are unknown. Now for BK is going to be, I'm going to draw the other forces that we don't know for BK. BK has two components. One in the X and one in the Y. But remember that? Agree? Alright? So BK is like that. I just tidying it up so that you can see it. Don't think I'll put other force there. It is just relative there. So that's it. So this is 36.9. Was it 36.9 by the way, guys? It's not 36.9. You know why, guys? Almost get caught. We need to go back to the geometry. Before we move on, we have to go back to the geometry and check it. Check, 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 check. Look, this is 2 here. And this is 3 here. So it's not the same geometry. If you use that, you're wrong. Have to make sure you check your geometry. That, remember I said it before? Almost caught me. Trying to sail on quickly. All right, so let's check it. So this is what? This is 2. BC. 2 and K is what? 3. So that is a 2-3 triangle. So if you get this angle here, theta, is tan theta is equal to 3 upon 2, which is 1.5. So tan 1.5 is how much again, guys? Tan inverse of
56.3.
come again?
56.3.
So the angle sub 10, you're looking for my right eye, I cannot find it. It's gone all over. Where is it? Oh, so theta is 56.3, right? So guys, if you use the one assumed before, you need to check the triangle, right? So that is a killer, right? You must be careful not to be caught by it here. And so it's a lucky thing. Oh, so you know, because I was looking at the figure up there, so I almost made mistake to write it there. So this angle here is 56.3. And that's the only one we have there, right? Yeah, this one is also 56.3. This is really the one. So, right. So they're the corresponding triangle, right? So, and therefore now we go ahead and we're gonna just do like before. What is this one down here? This is BC down here. Let me put it down here because him kind of bulky up there, so we don't want him up there. So we can actually write the component. So this is F, BC. So this component is gonna be F, BK, cos 56.3, while this one is F, BK, sine 56.3. All right, so let's go ahead now and apply our equilibrium equation. So if you apply our equilibrium equation, we're gonna say which one is advantageous for us. Do we have the one coming down? It was 4. So we need to put it in 4 kilonewtons. So let's see, we have 1 coming down. So we're gonna do the y first because we have 1 known and 1 unknown. So that is advantageous. So we're gonna sum all of our forces in the y equals to 0. And when we sum all of the forces in the y equals 0, right? We are going to go ahead now. So we have -4 plus f bk sine 56.3 equals to 0. All right. And so our FBK is going to be equals to 4 divided by sine 56.3. What that gives us now, guys, can you somebody work that out for me?
4.8.
4.8. Any more decimal?
07.
0. All right, 4.1 kilonewtons. All right. So we done that one. Next one now. We're going to go for the y now. Where's my pointer? I can't see this pointer sometime. All right. But I don't want it too big. So some of the forces in the y now. Sorry, in the x, pardon me. All right. Oh, let's clean that up. In the x equal to 0. So let's go now. In the x, we have quite a bit of forces there. So we have, the first one we have is F AB. But it is what? Is it positive FAB or minus FAB?
Minus.
And I hope you recognize why it is minus, because it's in tension, so you must put it in the opposite direction. And then we have plus FBC plus FBK cos 56.3 equals 0. You agree with that? So this now, what is AB now? What was AB value? It was minus what? 13.75. Was that its value? Let's check it. What was its value?
Yes, sir.
When we found it first, it was right, but we're going in the opposite direction, so we have to change the sign. Then now, BC. Did we find BC? No, but we have BK, so we have plus FBC, and we have BK. BK is 4. It's positive, right? 4 plus 4.81 cos 56.3, right? Equals to 0. So what is BC now? So BC equals to minus 4.81 cos 56.3. And then you take that over, it becomes what? Plus 13.75. What is the answer here now, guys?
11.08.
So you get 11.08. Right? Some people say approximately 11.1 kilo newton. So therefore you have all of those forces. Right. And then now from that, you can typically now go to joint K. If you go to joint K, how many unknowns you have there? 2. So we could go to joint K. Didn't do this one before. What time we have?
Sir, go back up for a second, please.
We're gonna run to joint K quickly. Where? Here?
Yeah, thanks.
So joint K, how many unknown we have? We know LK, we know B, we know BK, right? We don't know BJ, we don't know BC. So we're gonna draw this one now. We're gonna do it on a separate sheet. So we're gonna let's do this again. Hold on, I don't want to copy it that way. Let's see if we can borrow it again. So yeah. We're gonna copy this. We could probably put it up here too, you know. If we can put it here. All right. I'm gonna put it over here. It's not advantageous, not helping me. Only thing I need from it is to get some information from it. The information that I need is really here. FBC. So I need some information. Let's see if we can accumulate some information. So FBC, FB, it was BC or B what? Let me see what it got to. FBC, what was FBC again? 11 something. FBC is 11.08. What else did we find? We found BK. BK, which is equals to, what is BK now? 4.81. 4.81. And they're all positive. Let's check that. They are positive. What about BK? Positive. What else did we find? We found LK. Did we have LK value here? FLK was minus 17.2. Right? Everybody remember that? So we have LK, BK, LK. We know LB as 0 already. Right, but we're not using that one. AL. We don't using AL neither. We know we need BK. We have BK value already. All right, so we're just making sure we have BK. All right, so we're gonna draw it now. Let's draw it quickly, in just of time. So we need to see it. I'm gonna draw it right over here. So we're gonna stick a pin here. All right, and we're gonna consider joint. So we are considering joint K. Too close. That's killing my space. So we're gonna consider. So we're considering joint K. Let's draw joint K quickly. So we have K here, and we're gonna assume that one is in tension there. That's not a good start. Do I have my writer? Right, yeah. This is K. Then we're gonna assume one going down. Tension. I don't know if it is that way. This is C, that way. What's the next one I have? I have one going here. What was LK again? LK was compressive force. So it must be going in the joint. All right. Oh, come on. LK going in. We're gonna assume that LK. So we're gonna put it compressive and change it. Right. So it is FLK, and we're gonna put it value as 17.2 because we change the sign, change the direction. And then now this is now known as F. This is J, so it's FJ. What did I ask us to find? JK, same thing. Alright? And then now what other force? So how many other force left out now? One more. BK, we found BK. BK was a what? A tension force. BK was a tension force, so we have to draw it as a tension coming out of the joint. Alright? So it's a tension force. Right. So that is, we keep those values. Alright. Alright, so this is not a, so we know the angle that this one is subtend. So this has an angle to the horizontal that we know already, we established. What was the angle for this one? This was 53 something. 53, how much was that again? 53, where's the value for it? 53.6, 56.3, 56.3. While this one was the other angle. This one was another color. This one has a, this was 36.9. All right, very, very important. All right. This label, let's label them. What did I say? I should have labeled them same time I was calling them out. This one was this is C. No, this is B. Oh Lord, I can't find them. This was B. So let's check that. Am I having them right? How many forces I have here? I have, oh, one is L, one is L, one is B, and this one is C. C could actually come down somewhere to be practical. All right, look more proportional. All right, and then now I need to write the forces. So this one will be F, K, CK or KC, right? Probably CK. That's the best way. But I write them from the direction it's coming from. So this is FKB or BK. And this one is F LK. Right. Right. So you could call it CK, it doesn't matter. You could call it CK. No matter seriously. BK. And this one is BK. I think that's how we had it before. Yeah. Be consistent. FBK. FB. All right. So there we have them. So we have, this is a right angle here, and we know the rest. So let's proceed now. We have all of the forces. We change one of them direction, right? Which one we change the direction again? I'm trying to remember. It's the LK1. Okay, so remember we're not using it as minus, we use it as plus. So this value here we need to circle. All right? So we're not using it as that value anymore. All right, so let's proceed. So now we're going to use the sum of the equilibrium equation again. Which one is a good one to start with? What do we know? We have one. What is, we know BK. Let's put in what we have. BK is 4.81. So we only have two unknowns. Beautiful. Now, if we go horizontal, how many forces we'll have what we know? We only have one if we go horizontal. You agree? What are the components here? Let's write some components. So we have a component here for this one, which is going to be F BAK cos 56.3. And this one,
Sir,
yes?
I have a question. That angle 56.3, I'm getting something else. To get that angle is not tan inverse of 5 divided by 2?
5? Where you get 5
Mm-hmm.
from? Where you get 5? We get 5.
Because you're taking that 5 from the back of the 3, 4, 5 triangle you made
I'm
before.
having 2 here, and I'm having 3 here. You see it? That's the triangle I'm working with. So
But
I
wouldn't
can't
that
get
be
anything
5?
different. So I can't get anything different. I have that. This is K. This is B. And this is C. You see it?
Wouldn't that, so it wouldn't be
This is
5.
2. This is 2. And this is, I'm not going all the way down. No, there's no 5. There's 2 and this is 3.
Oh,
You see what I'm saying?
okay.
That is the triangle that I am interested in. That's the right angle triangle I'm interested in. All right?
Hmm.
All right. And then the height of this, what's the height here now? This one up here, this one here would have been FBK sine 56.3. That is that one. I won't even try to write in the green one because the green one, I don't want to confuse person. Let me see. I can't find the green when I put it in green. Oh, it's so faint. So this is F LK cos sine 36.9. While this one is F LK cos 36.9. So that is why I'm trying to write them is to try and show you that they're all there. Maybe I use a wrong green. The green that I use is kind of too neonish. All right, let's go back to the black. So all right, we are going to go. Which one did I say I'm going to use? I'm going to use the horizontal. Was it horizontal? If I go horizontal or vertical, let me see. If I go horizontal, I find KJ immediately, or JK, whatever they want. So let's go with that one. We're gonna go horizontal. So sum up the forces in the X equals 0. So we have and the direction. What's the directions now? The first one is still going this way. So it is F LK cos 36.9. And then the other one now is going the opposite direction. What's the component going? This one is going down. And this one is going negative. You see that? So this one is going minus F BK cos 56.3. Right? And then the latter one now, the last one is going to be going positive direction. F KJ equals 0. So we need to look the direction where the force is going in order to write them. All right? So let's put in your value. LK is what we have it as. LK, we had LK value 17 point. So this is 17.2 cos 36.9. While BK, what was BK again for? So it's minus, I will put in the value, 4.81. Why it become minus? Because of the direction it is going. Right, cos 56.3 plus FKJ equals 0. So work out that now what you're getting, folks. And the first one is saying 17.2. Please work them out for me. Confirm the answer. So the first one is 13.7 something. 75 minus, what's the next one now? 4.81 cos 56.3. How much you get for that one? 2 point something? 2.66
2.67.
plus FKJ equals 0. So this one is gonna give you that FKJ is equal to the difference of that, but the sign is gonna change. One is become minus, one become plus. 668. So it's a minus value, it's a compressive value. What's the value we get here for that?
Negative 11.08.
Right. So we get that kilonewtons. And then the latter part, and then which other one we have we didn't find? CK. All right, how we find CK now? Same thing, make it a little bit smaller. How we find CK? What? They didn't ask us for CK, but they didn't ask us for CK now. But CK, if we find CK, we would have found everything. All right, let me just so CK, let's write it down fast. Time is going on me. So this next one, sum of the forces in the y equals 0. Where are we now? So we have one going up, which is FLK sine 36.9, positive for the LK. This one right here. All right, that component. And then we have one coming down, which is minus. Try not to make a mistake. This is F. What is this? BK. And this is sine 56.3. And then the next one coming down is minus FCK equals 0. I think we capture all of them now. So the first one is going to be, what's this value? 17.2 sine 36.9. And then what is BK now? Did we get BK and thought do we calculate BK yet? We don't just calculate BK. What was BK value?
4.81.
You sure? Yeah, 4.81 sine 56.3 minus FCK. So all we have to do is carry CK to the other side and work it out. So CK is going to be FCK one side and work out the others now. What work them out? So what we have?
10.33.
How much?
10.33 minus.
Minus 10.33 kilonewtons. All right. 10.33. How much you say for that one? Let me just check the value. K, how much we got for kg again? 11 point something. All right. And how much you get for kc? Did we find kc? kc. I'm looking for kc value. kc. All right. We're gonna check kc value. Did you work that out correctly? Was it supposed to be a minus? Check kc value for me. kc value. Let me see. Was one of these supposed to be minus? I'm checking. kc value. 7 points. LK. Did you put? You didn't put in a minus. So let me see which direction we had it going. It was positive. All right. And KJ. Hold on. We got KJ.
Sir, the value that I gave is not the complete answer, sir.
Oh, what answer you give me?
Oh,
Which one is
that's the
that?
value for the 17.2 times sine 36.9.
So the other one must be plus that.
Yes, sir. Plus
Or
the
plus whatever that is, plus says 4.81 sine 56.3.
It's 4.
4 point something, 4.000. So that now is gonna give me what now? 6 minus 6.33 kilonewtons. So there, so guys, we have all of the values for those. All right. With the interest of time and the time almost finished, I'm gonna show you method of section. So let me just stop that because that is all method of joint. Method of joints is long, guys. If we wanted to find all three before, it would have been just sweet. Oops, one go. All right, so let's show you method of joint. All right, better now than never. Let's get an extra page. Where did I go? I don't want it there. Let me go back here. I don't want it there. Go out. Method of joint section now. Let's do this one. So method of section. All right, so bear with me a little bit. I'm going to take a few minutes of your time. Not long. Method of joint. Now let me show you how method of joint go. Make it a little bit smaller. So I have to draw a free body diagram. I'm gonna sketch it fast. All right. So I have this beside me, and all right. So we already know the reactions. I will need those values. So we know we had a reaction here, which was what? 10.33 for the AY, and for this one, we know it was GY was 12.67 kilonewtons, right? We know those. Now you have to draw back your sketch, guys. So look, so you're gonna sketch him back. I'm gonna see if I can do it up here. All right. Oh, Lord, that is weak. So you're gonna sketch it back quickly. And you're gonna sketch back that. One row there. All right. Make a bit lean, that's all right. And then you have one here. Broken. Where am I now? You're gonna have one come down here. And then you have one here. All right. You have one here. Now this represents the section that is cut. Cutting plane line is here. All right. Now you need to do some labeling quickly. This is point J. This is K. This is D. This is C, force coming down. And this is reaction going in. This is a reaction coming out. 2, 2. This is A. B. This is C. And this is, so we have everything labeled now. This is what? L. All right. So this is 10.33, which is G. Right? This is 4. This is 5. All right. We label this. This is F. J. K, as we want to call it. This is F. C, J. And this is F. CD. Arrow. Arrow. Show the direction. So you assume that they are in tension. Now, when you do that, guys, you have pretty much the global forces. So you don't need to do anything else. Now you're going to just take some moment. So we're going to take some moment at some advantageous. 2 moments I'm going to take and find most of the forces. All right, 2 moments and 1 equilibrium occasion. Just bear with me. I'm going to need about 10 to 15 minutes of your time. A lot of persons gone off to sleep already, but let's run with it. You're going to take moment at J. So we're going to take moment. All right. And so a moment at J equals 0. Let's go now. Now, the dimensions are important because you have dimensions here. on a different color dimensions coming across. This down here is 3. Remember, the height is 3. These are 2, 2, 2. This is also 2. CD is 2, right? So all of that is important. So let's jump into it. You take moment at J, it means FJK and FCJ gone out of the problem. You're only left with FCD, right? So only FCD you want. So basically you're taking moment right up at where all of them meet. So the J is necessary. You're taking moment right there. All right, the unknown you have is FCD. From J, what's the distance of J from the 4CG? It is coming down, and that is 3. So it makes a right angle here. And it's going to turn it in the counterclockwise, which is positive. So remember our convention that is positive. So it's going to be FCD, right? That's probably 2, right? FCD times 3, first one. The next one, you have, remember is J, you're taking it from, so the first one, the 5. 5 from J is, what's the distance? 5 from J. So remember 5 coming all the way down to K, but it's at a distance of 2, right? So it's going to turn the body into the counterclockwise, right? So it's therefore it's going to be positive 5 times 2. The next one is going to be this distance here from J, which is going to be what? 4. So it's 2 more. So it's going to be plus 4 times 4. And for the 10.33, what's this distance from J? It's all the way coming down to 6. Right? So it is going to be plus 10.33 times 6 equals 0. And so all of this is going to be equal 3F CD is going to be equals to 10 come over minus 10 minus 16 plus, what's that? 60 something. How much is that? 10.333 times 6.
Sir, excuse me,
61.
sir. Why is the 10 positive?
Ah,
Why is the 10 positive?
thank you, sir. You know, you're looking. Thank you. Because I'm trying to sail on in interest of time. Yes, it's going the other way. Thank you very much. Thank you very much, sir. Thank you. At least one person is not just a spectator, they are participants. All right. So therefore, that works out to be how much, sir? Going too fast. So this is minus 25 plus 26, sorry, plus that. How much is that? No, what's the difference? So it's 26 minus that value. We're getting what? 35.98. That's all? And this
Yes, 35.98.
is FCD is equal, you divide that by 3. And you get what now? Approximately 12. Approximately 12 kilonewtons. A little bit less than 12, but I just round it after that because it's 11.99, right? And then the last latter one now, next one now, can I make it a little bit smaller? So the next one now, we want to take moments now about where now? We're gonna take moments about C, right? If you take moments about C, let's see what will happen at C. If you take moment at C, 5 gone, right? And you know Sham's gone again, FCD gone, and FCJ gone. Did we find FJK yet? We didn't find it by this method, so we're going to show you how to find. So it means that FCJ out of the problem and FCD out of the problem. So it's FCJ alone would have left. So let's do it. So therefore, FCJ, the distance from FCJ from the tree from C is 3. So, and it is gonna turn the body in the counterclockwise. You agree? Which is no, it's gonna turn it in the clockwise, which is minus. So it's going to be FJK times 3. And then the latter now, the only other
Sir,
thing I have left is a
excuse me,
4.
sir. Could you draw that?
Huh?
Could you draw that? Because I'm not visualizing.
Look, let me show you where it is. Let me try a color that is not readily used. Orange. So it is here. The force is coming down here. Let me see if I see this. Sure. The FCJ is here. Sorry, JK is here. You see JK?
Yes, sir.
But it is all the way here from here. 3. So this is where the right angle make.
Oh.
So it's going to
Yes, sir.
spin it. It's spinning it that way. You see
Yes, sir. I
now?
see it now. Yeah, I see it now.
So that is that one. And then the next one is the 4 force. The 4 is gonna be turning it in the counterclockwise, which is positive. So it's going to be plus. Let's get back the black or the blue. 4 times what now? 2. What about the 10? 10 is gonna be going minus 10.3, which is a reaction, times 4. Is there any more forces? No. That equals to 0. And so that is equals to minus 3FJK going to be equals to what now? Minus 8 times 10.33 times 4. That gives us plus 41. Let me get the 40. 41. I'm trying to go as fast as 41.32. And that gives you what now? So FJK is equal to the difference there. You get 33.32 divided by 3. So that is going to give you 11 something. 11.1. Was it positive? Yeah. No. It's positive. Hold on. If it come over, it's not supposed to be
It's
positive.
negative. It's negative, sir.
No, man. Hold on. It's negative.
Positive, because there's a
Negative.
negative
It's
3 and
negative.
negative on the other
It's
side.
negative. It's negative. Yeah, it's negative, right? Because that remains the same. I plot that over and I change it over, so it's minus. So therefore it is minus 11.1 kilonewtons. So that give you 11. All right. Only one force wasn't found. Let me show you how to find it. You don't have to take moment. It has 2 components, and you just need one of them. So it has 2 components. Let me just show you. It has 2 components. One in the X. Come on. One in the X and one in the Y. I don't know why this thing is drawing so crappy in the night. So it has 2 components. One in the X and one in the Y. Can I get it draw properly? One going there. One coming there. It's our decision now which one to use. Which one is more advantageous. I would take the horizontal because I have all of the others. So if I go horizontal, I'm going to go with FCD, which I have already, and I'm going to go with FJK. I should get this one here fairly easy, a component there, FCJ, which is really going to be what? The angle, we have the angle already. What was the angle? 50 something. What was it again? 56.3?
56.3, yeah.
Yes, I will know the component. So the component is going to be cos of that. So let me make it smaller so I can write it and then I'll come back bigger. So the component is going that way is going to be on the block. F, what is the component that we're finding? FCJ
Yes, sir.
cos 56.3. And then we have it plus FCD plus FJ. Those what? J is something we're finding. JK. Yeah, JK. And it's simple as that. So that is what now, that is the sum of the forces in the X equals 0. So that's what we use. And that is equal 0. So we have FCJ, make it bigger now. So FCJ cos 56.3. What was FCD again? FCD was what? 12. Let me check the directions. We have the directions, okay. Yeah. Plus J is minus 11.1. All right. So that should pretty much work it out. What's the value here now? So we're gonna add those two. What's the difference between that and 12? Hold on. So it's give us, so FCJ cos 56.3 is gonna be equals to it is going to be a minus 0.8933. So FCJ equals to minus 0.8933 divided by cos 56.3. And so what are we getting for our answer?
1.6.
All right, so we're getting minus 1.61 kilonewtons. All right, so that is once, if your signs are off, your answer gonna be off. Yeah, so that is how you do it. But so you see, method of join, method of section would have given us the problem quickly. So this is method of section. So that is method of section, guys. Done. All right. And how many steps we did it? Probably about 5 steps, and we get so you'll get full marks with 5 steps. Now, method of joints is have its advantage, but it's a longer process. Much longer process. But you have to systematically do it. All right. One of the difficulty that I had is because of the sheets. So I have to be working on sheet to sheet so as to navigate. All right. So I have them here, and I will at the end of the week, if you want me, I can post the video. Right. All right. For the rest of you who are here, I didn't do it for the rest. You can just drop your name in the chat for me, please. Just let me know persons who came to the session. Just drop your name in the chat before you leave. All right. And I trust the session was beneficial. The other one that is on the platform, guys, have a look through it. I will still give you the solution whether or not we go through it. All right. And I also post the solution here for this one.
So is this solutions available to us?
Yes, man. I will give you the solution. Anything that I do for the tutorial, I'm full solution will be available. All right. I will not put such a complex one in exam, but you will get one. You get a frame. If you can do these, then the one in exam is nothing to these. Both midterm, well, I may put one in midterm. I don't know yet. I haven't decided. But you know the midterm, you still plan for the midterm. I may put stress on the midterm. I won't go beyond stress. Yeah, I won't go beyond stress. I don't think so. And I won't put rigid body on it. I'll leave out rigid body for you. You'll see that in the exam. but I will midterm, you will get all the other types. So that's unit 7. I'm not gonna put unit 7 in your midterm, but I may put unit 8. Everything except, and I don't think I'm gonna put shear force and bending moment. Everything up to 8 except unit 7. So,
Sir,
oh, let me stop the recording. If you, yeah.